Algorithms are defined as step-by-step instructions to perform a task in a fixed amount of time. Algorithms have been around for as long as monkeys have climbed on trees and ants have created colonies. We have learned a lot by watching the patterns of nature and developed many algorithms based on this. An example would be the ant colony optimization algorithm, which is known for finding the shortest path through a graph. Weaver birds weave intricate nests from vegetation, such as leaves and grass. Once hanging from the tree, these nests can withstand blustery winds. Not only are they remarkable, these nests are built using patterns for functionality and effectiveness. As we have observed nature in its element, we have learned that natural algorithms generate solutions that are close to an optimal solution in a reasonable time frame. Conversely, computer algorithms are generally expected to produce the same result in the same amount of time given an ideal computer system in which to process. Thus, natural algorithms are naturally efficient. Finding an optimal solution for a problem depends on which factor we choose to optimize and make efficient, meaning we will attempt to find an optimal solution based on a certain factor, such as time or resources. Let's consider a building elevator and evaluate the efficiency of its travel algorithm. Let's assume the building has 20 floors. The algorithm that is coded in the elevator microcontroller is likely time efficient in order to select which floor it needs to service. This is dependent on the number of buttons pressed by the riders on different floors and the algorithm code, which should be designed to be the most efficient system for all riders. One possible solution would be to use a queue consisting of the first-come, first-served method. The first rider who pressed the button would be serviced first, followed by the second person who pressed the button, and so on. This is not the most efficient nor effective method to use. In fact, this would make most riders very unhappy as they wait for the elevator, only to find the elevator skipping their floor to service the first rider, then skipping their floor again to service the second rider, and so on. Based on the unhappy riders kept waiting, let's consider optimizing the total distance the elevator travels to save energy. In this scenario, the riders press the up or down button on their floor, and once inside the elevator, they choose their desired floor. The elevator will take all the riders in the up direction until there are no more floors selected. Then the elevator will service the riders who press the down arrow and are waiting for the elevator to take them down to their desired floor. Assuming the elevator goes all the way up and then all the way down, only to repeat each cycle, it's likely everyone will be pleased since the elevator eventually goes in their desired direction. However, if you just missed the elevator on the first floor, you may have to wait a long time. So let's try something else. What if riders key in their requested floor outside the elevator? This allows the elevator to optimize the total trip for energy efficiency. Some people may wonder why the elevator is taking them up and down on the same trip. It's likely the riders will get upset because the elevator is taking them in different directions despite the elevator saving energy. This would allow the elevator to have a better routing algorithm because it is energy efficient. Changing our focus, what if we optimize for total time wasted by people at and inside the elevator? Again, the elevator might go up and down to minimize total time, but people would love saving time. However, you would need to explain the intent of the process. Otherwise, they would complain about going up and down so much. What if we deploy a machine learning algorithm for the elevator that can learn from the behavior of riders in the past and present environment? The goal is to minimize the sum of the waiting time and travel time of the rider, which should bring the most satisfaction to the riders. This desire is human nature inspired. This is an example of a non-deterministic polynomial time problem, or better known as a NP-complete problem with no deterministic solution. This means no efficient solution algorithm has been found for this problem. But we can apply the ant colony optimization algorithm to find an optimal service time for the riders. We can develop an approximate solution just like in nature. In this video, we have taken a human nature-inspired problem, such as servicing riders on an elevator, and solved it optimally with an ant nature-inspired algorithm.